the protein side, right, as we discussed earlier. So, the sequence ID is very high, identity is 84, positive is 92%, right. In this case you can do the homology modeling, right. So, you can see the homology modeling here. This is the one is SRC kinase and the blue one is a CS kinase, and the RMSD is 1.09 angstrom, right. So, what is RMSD? Root mean square deviation. How far these two structures when you superimpose, right, they are vary from each other, right. This is 1.09 angstrom. So, you can see Ramanathan plot most of the cases in the allowed region. So, you can see the structures, right, they can validate and see okay structures are in good shape, right. Once this is done, you have the one static structure. Now, we need to do some dynamic structures, some different conformations. In this case we can do molecular dynamic simulations. So, what the MD works, how MD works? So, you can apply some temperature and pressure and a different time frame, you will get different types of structures, right. So, we can use various packages available in the literature like Amber or the Gromos, right, so different force fields, right. You can simulate the particular protein, right, and at various time frame you can get the conformation, right. So, you can see once we get several conformations, right, these are the conditions used for getting these structures, right. So, finally, we use sampling. Once we do with the different conformation with the conformation clustering, you can cluster using nearest neighbor method. What they do? First they count the number of neighbors, any specific cutoff we can count the neighbors. Then they take the structure with largest number of neighbors with all the neighbors as a cluster, similar type of cluster. This is what how the clustering works. Then eliminate it from the pool of clusters and remaining the repeat for the remaining clusters in this pool. So, likewise you can create several clusters and from these clusters you can identify the sample structures, you can use it for the docking. So, if you use the 10 nanosecond trajectory with 10 ensembles, right, you can get the 20,000 conformations in the interval of 5 picoseconds, right, because even if 5 picoseconds go with the 100 nanoseconds, you will get about 20,000 conformations, right. 20,000 conformations using the clustering techniques, we made 10 clusters, right. Take the protein, do the MD simulations with the different time frame, right, for example 5 picoseconds, get conformations and like arrange the conformations in different clusters. We have 10 clusters and we look at the 10 clusters, 7 are open conformation and the 3 are in the closed conformation, right. So, if it is an open conformation, then the ligand go and bind. If it is a closed conformation, it cannot bind. So, this is not good for the docking. So, that is fine, right. So, if you see this is the cluster number and this number of frames, okay, some of them these 3 are the closed conformation. So, we take all the open conformation data. So, we have 7 1 2 3 4 5 6 7, right. You can see C2, C5, C6, okay, this is okay, fine. Okay, here you can see the superimposition of all the 7 structures, right. Some of them are here, this is the ligand binding site, you can see the superimposition of the structures. So, 7 conformation you can see the 7 structures 1 2 3 4 5 6 7, this is homology modeling one and here this is the actual one, right. We have 9 structures. So, protein side we have now we had set 9 structures and the ligand side, how many ligands we have? Around 11,000 ligands, because 5,000 from this library and some decoys and the known actives, right. But now we can do the docking. So, if you know the protein, so we know the active site, there are several residues the active site, for example, these are the main residues, valine 281, lysine 295, glutamine 339, 41, 86, ARG 88, aspartic acid 404, tyrosine 416. So, now you can generate a grid around these active site amino acid residues, because the ligands probably they potentially they bind only that region, right. You can generate a grid and you can use all these 11,000 compounds, right, to dock kind of virtual screening. So, in this case we can do the high throughput virtual screening or you can do a standard precision and the extra precision available, they are available in the glide module in the Schrodinger. Okay, then finally they get the score, right, using this equation, right. Glide score is given as, okay, there are different components, this is a Coulombic interaction and we have the van der Waals interactions, here this is a lipophilic interaction, this is hydrogen bonds, this is the penalty time, right, given for the burying the polar functionality in the hydrophobic environment, because if we have the polar residues, the mainly the surface interact with the residues of the surface. If it goes to the buried ones, then we give some penalty, right. Here you can see the rotatable bonds and you can see the other interactions, right. So, we get this Clyde score to get the interaction between protein and the ligand. So, most of the cases we get good score, but here they already optimized with some numbers, right. So, in this case it may also have some chances, right. So, that it may fail to identify the best hit also, because it is optimized with some set of data, fine. So, now how to get the hits? So, we can use the Clyde score and we use with different types of screening. We can use the high throughput screening and with the standard precision and the extra precision. So, each case you can get some data and you can rank all the data. So, you can see the best of top 5 hits from all the screening methods, that is a 7 MD and 1 homology model structure. So, 8 methods, right, and 8 screenings you can get 5 hits. So, we will get 40 hits for the virtual screening, likewise 40 from this standard precision and 40 from the extra precision. So, totally we will get 120 ligands, we can see the 120 ligands, right. So, we get the MD derived structure 7, homology model structure 1 8, other side we have the ligands. We have 3 different types of screening methods, each method we take the top 5. So, that means 8 proteins into 5 equal to 40, each different screening method 40 40 40, that will be 120. So, this is 120. So, if the Schrodinger could get the best one, so the top one should be at the topmost one, right. But if you look into this experimental data, these are the ligands which showed some potential inhibition, like ranked number 18, 32 and 105, right. So, you can see this here, these are the compounds which are identified to show some sort of inhibition, right. They are at these different ranks 18, 32 and 105. At least we can see all these compounds in the top 120 hits among these 2.2 million, because we rank from 2.2 million we get 120. Among these we can see the 3 compounds which are at the in the list of top 120. Okay, now we will see the how they interact and how they could be a potential lead compound. So, take the one which rank 18, okay, this is the one rank 18, this showed the inhibition rate of 26.9. So, we have the Clyde score of 10.42 and the energy of minus 62.8, right. So, the difference between score and energy, right. So, the score means they have this empirical equation to get the value by combining different factors to put the empirical equation and finally get a number, that is called the Clyde score. Energy, they calculate the van der Waals energy and the electrostatic energy like the ampere force field, then they give the total energy of the system. This is the this energy using the Clyde. So, here the inhibition is 26 percentage, right, and then see this is the compound and you can see they surrounded with the protein amino acids in the protein. So, some of the interactions I will show here. Okay, you can see these hydrophobic interactions and some of them are having the hydrogen bonds. You can see this is the OD1 and this N2, they are having this electrostatic interaction, and you can here also you can see the interaction, right, and here are the hydrophobic interactions, the CH2 groups. So, these interactions are mainly dominant electrostatic and van der Waals interactions, right. So, Clyde score is minus 10 and the Clyde energy is 62. We check the contribution, van der Waals is 41 and the Coulombic energy is minus 21, right. If you add up these two, you will get the 62. Then we can compare the compound, this is the compound we obtained from CS kinase with our molecule, our compound, this is the zinc ID for the compound. If you see the crystal structure, there is a similar type of compound available with the CS kinase and ANP, right. So, in this case you can see the interactions, mainly the lysine 295, okay, these are interactions, and tyrosine 416. Those T interactions are main interactions when this co-crystallize with the ligand ANP, right. So, you can see similar type of interactions with the co-crystallized structure as well as the one we identified using virtual screening. Then this is another one, this rank 32, right. Here the inhibition rate is 24.8%. You can also you can see the type of interactions, right. You can, this is the ligand and you can see how they are interacting with the amino acids in a particular protein, right. So, this is another one rank 105, this is also inhibition 24.8%, and here you can see the interaction electrostatic interactions as well as the hydrogen bonds and other hydrophobic interactions for this particular ligand. So, the score is minus 8.8 and the energy is almost similar, that is minus 64.21 kilocalorie per mole, right. So, now this is one step. So, here what we did, we take the protein side, take the ligand, get the properties and reduce the number, do the screening, and then we identified the probable ligands. It is also possible to look into this binding site information. For example, if they have the kinase inhibitors, right, because we also in the first competition we also learned the probable potential compounds. So, they classify two different types, one is type 1 and type 2 based on the competition of the ATP. So, in this protein, right, if you see there are two different conformations, one is the DFG in, okay, you can see the here this is a DFG motif, okay, right, D is aspartic acid, F is a phenylalanine, G is the glycine, you can see here. So, these DF motifs either it is in the ATP binding pocket, or if they block the ATP binding pocket, now there is the allosteric site here, that is the competitive inhibitors. So, this protein they have two different types of motifs, right, one is the DFG in conformation, in this case type 1 inhibitors bind with in conformation and type 2 inhibitors they bind with DFG out conformation. This information you can obtain from the literature, right, and the movement of the activation loop to this out conformation also exposes an additional hydrophobic binding, right, directly adjacent to the ATP binding site. There is another hydrophobic binding site adjacent to the ATP binding sites. So, in this case if you know the conformation DFG in or DFG out, even if the homology is less, structure wise you can get a similar structures and you can model the structures and mainly focus on the conformation. So, here this is the two conformation, right, one is DFG in, one is DFG out conformation. This example, one example is ABL1 kinase, okay, this is the complex with the ligand, this is a kind of type 1 inhibitor, that is ATP competitive, this is in DFG in conformation. So, this is the PDB ID for that particular protein. Likewise, this is another complex ABL1 kinase with imatinib, this is a type 2 inhibitor, this is in DFG out conformation, right, this is the template. If you see these two templates, the sequence identity is less, but the structurally these binding pockets are having similar structures. So, then we can easily model the structures with the CS, right, you can see the RMST is very less, right, at this particular region, right, in this region, this is the in conformation and this out conformation. So, now here we have only two structures, earlier we used 8 structures, 7 from MD and then 1 from the homology modeling, right, then we use a screening. So, here now we have the two conformation, in conformation, out conformation, and as I discussed earlier we need to prepare the same, right, you can prepare the ligands, right, and get the properties and we can filter with the average property values and then we use a Tanimoto coefficient. So, we do everything the same, then do with the screening, right. So, you can see the in conformation we will get about 76,627 hits. Likewise, if we take the DFG out conformation, so we can get about 75,000 hits, then we add up together, now we will get about 1,000,000 compounds, right. Then what we did, so those we are subjected to pharmacophore based model. So, what is the pharmacophore based model, right, if you see a protein you can see the active site and see the moiety, right, around this particular binding site. So, what are the features, right, corresponding to this ATP based moiety. So, in this case if you see what are the possibilities of different types of compounds. For example, here A is the acceptor, D is the donor and H is the hydrophobic and R is the aromatic ring, right. So, this is another example for the DFG out, this is the alignment of imatinib, right, and you can see the pharmacophore model for the compounds, right, which prefer the out conformation. So, now we have the ligands, you screened these ligands here and see which ligands they fit with this pharmacophore around the active site, right, based on the acceptors, donors, hydrophobic as well as aromatic rings. So, here also we know that ATP competitive inhibitors, here also we know the out conformation, right. So, how we fit the ligands, right, around the pharmacophore of this particular site. So, when you do this, then we will get different numbers and we can rank that numbers, right, using the fitness score. You can see here this DFG in and you can see DFG out. So, these are the ligands which fit the pharmacophore, right. So, first you can get the fitness score, you can screen, you can rank the based on fitness score, then go with the structure diversity. For example, if you have the 5 ones, they are similar structures, high scores, then take only one. For example, 1, 2, 3. So, they have similar structure, okay. Then you take the first one, right, then taking everything. So, then you can see check the interaction between the CS kinase and the ligand, actual interactions. So, you have to use various criteria to identify the top hits. One is the fitness score based on the pharmacophore modeling, and check the diversity of these compounds and then see the actual interaction between the ligand as well as the CS kinase. Once we do this, then we can have the compounds, right. In this case we could find 2 different compounds, the inhibition rate is very high. In the first case we prepared the protein, prepared the ligand and we did the docking with different screening, but we did not consider the conformation, whether this is binds with the ATP site or it is the competitive site. So, we did not consider that. So, there we got the maximum inhibition of 31%, but here now we consider the conformation and the type of inhibitors. Now, you can see this compound shows about 64% inhibition. You can get the score minus 12.88, the glide score, and the energy of minus 6.44 kilocalorie per mole, right. So, this is from the DFG in conformation. Likewise, you can get the another data. So, here this is showing 49% inhibition and previous DFG out conformation, right. So, here the score is minus 10.16 and the energy of minus 71.05 kilocalorie per mole. So, if you see the structure here, so in this case you can see this is the pharmacophore, it contains different residues and you can see the different types of interactions, right. You can see the hydrogen bonds, you can see the hydrophobic interactions, see phenylalanine 272 and this is a ring, this can form these pi interactions, right, and you can see this is NH with this one, you can see the hydrogen bonds with the serine, right, you can see different types of interactions. This compound also you can see the different types of interactions from these negative charge residues or the polar residues as well as the hydrophobic residues, right, fine. So, do the virtual screening, right. So, what are the various steps we have to follow to identify the potential compounds from the pool of compounds?
So, we need to have a library first.
Yeah, so first we need to have a library. So, ligand library we have. So, right now if you identify any specific target, we have to know the structure, right. So, 2 types you can do. If you know the structure, we can directly use the structure. If the structure is not known, then what you have to do? We have to do homology modeling. In this case we consider 2 different aspects. One aspect is we just get the sequence identity with the same family, similar same family, right, SRC kinase, CS kinase, right, FIN kinase, same family we did the homology modeling for the sequence identity. So, then we picked up the templates the same family, then we did the homology modeling, right, based on the template, right. Then they can see the validate the structure, right, and then if it is fine you can use it. And the second aspect, how did we get the structure? Here we mainly consider the conformation. So, DFG in and DFG out conformation for the 2 types of inhibitors, inhibitor type 1 and inhibitor type 2. So, because they are experimentally shown that this type of inhibitors they mainly bind with the particular site. In this case, even if you do homology modeling all this process, right, this is because they do not bind anywhere, they bind only that particular place. In this case you can focus on that region with the high sequence identity, right, we get similar structures and focus on these 2 conformation 2 sites, right. Mainly you can see I showed this here DFG motifs, okay, this is ATP binding pocket and this allosteric site, here we focus on these 2 sites, fine. So, now protein side either homology modeling we can do plus MD simulations. Why do you need MD simulation?
To get more conformation.
more conformation, right, because otherwise you have only one conformation. So, possibly many ligands may fail, because this case you can focus only one conformation. So, we made different conformations. So, did MD simulations and we get 20,000 conformation, classified in different clusters and picked up the samples from each cluster, right, because we omitted the discarded the closed conformation, because closed conformation ligand cannot bind. So, we take only the open conformation, fine. So, now the protein side we did two different aspects is done. Now, ligand side what we do? Right, first we have to get the known actives from existing databases, right. So, we get the known actives from the existing database, right, then we get the properties for that actives. Then the whole library, first we have to prepare the ligands, we get atomers and other charges and ions and all, and then we calculate these properties and we compare with the known actives, right, with some standard deviation. If these known actives and the known ligands vary very much, then we can discard. So, if any particular deviation, if you take any of the all the different properties they fit, then we can filter, make the first filter and get the compounds. And then what we do? Then we add some decays and some known actives as a control. So, we need to know whether the final result, we should identify all the actives, but should not get any decays. Then add up these compounds with the filtered compounds and finally use a screening and we will get the compounds. Then we rank the compounds and we can get that. That is from the homology modeling. In the second type, if you focus only on the sites, right, the type 2 inhibitors and the type 1 inhibitors, right, at these different sites, right, then we focus on that particular region. Particular region you can develop the pharmacophore models, and based on the type of residues with respect to hydrogen bonds and acceptors, donors, hydrophobic and aromatic rings, we can fit all the ligands and see which can fit, right, this model, and we can select based on the fitness score. So, if we get the fitness score, we can rank the compounds. When you look at the compounds, many of them are having similar structures. So, in this case, if one fails, 2 will also probably fail, 3 will also fail. If first 10 compounds, right, the high ranked compounds, and 10 compounds are structurally similar. If the first one fails, then there is high possibility that all the 10 will fail, right. So, in this reason, to avoid all this confusion, we take the similar structures and check the interactions and take the best and discard all the 9. Likewise, you can see the diversity to select the compounds. Then once you select the second refinement is over, when you select the compound, then you exactly see the interactions between CS kinase and the ligand, how they interact. Then if you are comfortable, then we can rank based on this order, right. Finally, you can select these compounds. So, then we compare the experiments, you can see the direct interaction between the ligand as well as with the amino acids, and you can see the good type of interactions. For example, here this 12.88 score and the energy 60 and you can see 64% deviation, right. You can likewise for any targets, right. So, we need to prepare the protein, prepare the ligand, and first collect the experimental information as much as possible, either the activities or the binding mode or the binding pose or if any specific residues which are involved in the active sites, collect all the experimental information as possible, so that you can finally validate the final model. If this is not properly interact with that particular residues, then you can discard, right. Then second, you can validate with the MD simulations, right, do the different MD simulation structures. In this case also you can see whether this particular ligand can fit at the different conformations using MD. But eventually for everything you need the experimental validation, right. It is very important to have the experimental validation. Once you do the validation, then you can see the percentage inhibition as well as the inhibitory constant like the IC values and so on, right. In this case you can go with the next level, right, the inhibitory studies and the animal studies and then final studies and so on, right. So, what is the advantages having virtual screening?
Less number of compound need to be screened.
Yeah, you can narrow down the compounds, right, to less number of compounds, so it can be easily screened. Otherwise, instead of doing 2.2 million compounds, so in this competition, right, several groups they participate in this competition, and different groups they showed the compounds which are totally different, right. The not many compounds are overlapping in different groups. So, then this case they selected the compounds 120 compounds from different groups, right. If 5 groups means that is about 600 compounds, they screened about 10,000 compounds instead of 2.2 million compounds. But in that case they could find about 25 to 30 compounds which are showing a high inhibition rate. So, instead of doing 2.2 million compounds, right, using the computational strategy, they use various methodologies. They use machine learning techniques, they use the pharmacophore based modeling, they use ligand based modeling, right, and they use the structure based drug design, and based on different approaches they identified the compounds. Finally, they could get some of the potential novel compounds as lead compounds and this could be as inhibitors. So, we discussed about the docking, we discussed about the screening. So, we can also identify the potential inhibitors using the QSAR studies, right. What is QSAR? Quantitative structure activity relationship, right, that we will discuss in next class, right. If we have a large number of ligands with known affinity for any particular target, then we can use the QSAR studies to fit the model, and using that we can identify new compounds, that also we can experimentally verify whether these compounds could lead as an potential lead compounds for as any inhibitors. That we will discuss in the next classes. Thanks for your kind attention.